Hello, everyone, and welcome to the July Recreational Astronomy Night Meeting online edition of the Royal Astronomical Society of Canada, Toronto Centre. My name is Paul Markov, coming to you from Markham, Ontario. And aside from introducing the speakers, I also search for presentations for upcoming meetings. If you have a presentation in mind, please get in touch with me, as we have openings for the August and later meetings. And a reminder that the meetings are now held on the first Wednesday of each month. Before we start the presentations, I'd like to thank in advance tonight's technical team that's comprised of Andrew and Betty Reed, Emma Seabrook, and Ward Legros. Thank you guys for making these presentations possible for us. As usual, we have 3 presentations this evening, and I expect we will be done around 9:30. The speakers are Arnold Brody, The Sky This Month. John Percy from the University of Toronto will talk to us about variable stars, recreation, investigation, fascination. And Trevor Jones, who is a video blogger at astrobackyard.com, will speak to us about deep sky astrophotography, proven methods for better images. And finally, Tom Luton will close the meeting with announcements. If you have questions, please enter them in the YouTube chat box, and Emma will ask your questions to the speakers on your behalf. Also, if you are attending the meeting for the first time, whether you're a member or not, please say hello in the chat box and let us know where you're from. So let's get the meeting started with Arnold and The Sky This Month.
Well, thank you, Paul. It's my pleasure to do The Sky This Month from my home in Whitby, Ontario, which is about a half an hour east of Toronto, on a good day. I'll be covering the period from tonight to August the 3rd. That leads us up to our next meeting. And the dates and times in my presentation are based on the Eastern time zone, and I'll be showing the sky as seen from Toronto. Now, the nights this month will be warm. Buggy maybe, but warm, and full of wonderful targets like star clusters and nebulae and double stars scattered along the Milky Way and globular clusters on either side. The gas giant planets are back, and there are meteor showers too. But before we discuss all this, I want to give you 2 mission updates. Is this the end of the Hubble Space Telescope? Well, that would be the worst case scenario following the failure of its main computer last month. Hubble is unable to continue doing science operations. NASA is working on a plan to switch the 31-year-old telescope to backup hardware and will test it on a high-fidelity Hubble simulator later this month. If successful, they will execute the plan on the telescope itself. So please, keep your fingers crossed. Now, back in December 2019, Boeing attempted to dock an uncrewed Starliner capsule at the ISS. And after reaching orbit, a mission clock decided it was time to start orbital insertion. But they were already in orbit, and so much fuel was wasted keeping the craft under control before the error was fixed that Boeing scrubbed the attempt to rendezvous with the ISS and brought the capsule home. So they will try again on July 30. On to observing. Well, if you are new to astronomy or wanting to expand your knowledge of the night sky, the RASC has developed 8 observing programs to help. And here are 5 of them for new and intermediate level observers. On the far left, the Explore the Universe is open to RASC members and non-members both. And for newcomers watching tonight, this program will help get your observing off the ground. The pun was intended. And I'll refer to the other 4 as we talk about observing this month. But regarding the Messiers, the middle program here, most Messiers also have new General Catalog NGC numbers. The program next to it, the finest NGC, includes 110 bright NGC targets that are not already in the Messier list, just to clear that up for you. I will upload a JSON file to our website. That's going to contain bookmarks for the targets I'll be discussing. You can import that file into your copy of Stellarium and then use the bookmark feature to easily jump to them. Seeing them in the sky, however, may be challenged by wildfire smoke spreading eastward from the devastating fires that are raging in Western Canada and the US. The smoke will reduce transparency. You may want to keep an eye on these two websites on the screen here to monitor the situation. Tonight, we are only 17 days removed from the summer solstice, so the nighttime window here in southern Ontario is brief. There's only 4 hours of true darkness this week, so pulling off an all-nighter is easy. Night grows to 5.5 hours by August the 3rd. And for observational astronomy, well, you can enjoy an extra 90 minutes to 2 hours by including astronomical twilight, when it's dark enough to enjoy the planets and double stars, for example. At local noon, the sun is about as high as it gets, 2/3 of the way up, when we look through only 1.07 air masses. This will help you see convection cells, filaments, and fine details around sunspots through the appropriate solar filters. Best time of the year to do that. Now, in this magnetogram image taken by the Solar Dynamics Observatory, green positive areas lead yellow negative in the northern hemisphere, while the opposite is true in the south. And these are the characteristics of solar cycle 25, which over the last week has started to ramp up significantly. Now, when the positive and negative charges intensify, it can generate sunspots where the field lines concentrate as though the ends of a horseshoe magnet have breached the surface. And they are colored red for positive spots and blue for negative. And this intensity gram taken 10 days ago shows those spots in black and white. And 10 days later, that same region, AR 2385, it moved over west of the meridian. And on that same day, Jeff Booth took a great photograph of that sunspot on the same day. Now here is my weekly alert from SWPC that I receive in my inbox every Sunday night that mentions last week's activity. Storms are not expected in the upcoming week, but that can quickly change. The R3 storm that occurred last week came on the 3rd of July, and on the day before, there was no sunspot at that location. In other words, the sunspot responsible for that storm rose to the surface in just one day and immediately began emitting M-class flares. So it's possible that there could be activity next week. You never really can tell. But if you want to subscribe to the service, there's this website down here. You will get these emails once a week on Sunday nights, but if something dramatic happens, they will send you an email immediately and not make you wait till Sunday night to find out. Now here's an animation from NASA's DialAMoon page that's on their Scientific Visualization Studio. It shows the moon's phases, libration or tipping action, and apparent size changes between perigee and apogee. You can visit the website on this slide or just search for DialAMoon. And you can get that website easily. And at the top of the page, you can get high definition stills of the moon for any date and UT hour you choose. Features along the terminator are labeled like they show on this image here, on this video. So you can take a printout of the still with you out into the field to help you identify the features that you are studying along the terminator. If you're out before sunrise tomorrow morning, you can study the southwest limb of the moon, which will be tipped favorably in our direction. And 2 weeks later, as the moon approaches full, libration tips the opposite northeast limb our way, giving us a really good opportunity to study the Betelgeuse crater and Heian that's pressing up against its northern wall. And nearby is Mare Humboldtianum. This is the best opportunity you'll have to study this area, which is also known for the Compton-Belkovich thorium anomaly. And that's due to the concentrations of radioactive thorium from volcanic activity when the moon was young. Now, this is of key interest for moon expeditions. In a 2009 team report in Nature by Peter Schubert, he wrote, "Thorium on the lunar surface can be transmuted into fissile uranium suitable for a controlled chain reaction to provide heat. Thorium is fertile, requiring bombardment by neutrons to become a suitable nuclear fuel. Well, that's interesting to think about as you study this area. Can you envision maybe a mining operation or an operation to gather the thorium, maybe a nuclear facility there to bombard it with neutrons and then take that uranium to maybe other locations on the moon where there may be colonies in the future? Something to consider as you study that area. At perigee, the moon appears about 12 degrees larger than at apogee. Did you know that's also the same ratio as the nickel and the quarter, both Canadian and US mint? Outreach tip, have these coins on hand to easily demonstrate the ratio between perigee and apogee moons. And speaking of the moon, it's going to be full on Friday night in 2 days. So the window for deep space observing is open right now and will run for another 7 days or so, and then returns at the start of August. And the full moon on the 23rd, it occurs just 2 days after perigee, so it's not really a super moon, though fairly close. This full moon does go by a host of names, most commonly the buck moon, since the antlers of young buck males, male deers are growing at their fastest this time of year. It's also known as a thunder moon for obvious reasons. Red asterisks identify dates when interesting moon or planetary alignments occur. I'll get to those in just a moment, but first I want to remind you about the globe at night. Now, you may remember that Chris Vaughn encouraged us at last month's meeting to print off charts and take them outside to compare the stars in the charts to your sky. Well, I'd like to encourage you as well to do that for the upcoming full moon, new moon season at the beginning of August. At that time, Globe at Night will be using Cygnus area and the summer triangle stars of Deneb, Vega, and Altair as the region to take a look at. So what you do is visit the website at the bottom of the screen here to print off these charts. Take them outside with you when you go observing at new moon at the beginning of August, and wait for your eyes to dark adapt, use a red light to study these charts, and then decide which one of them matches your sky overhead. The next morning, just key in your results. And as a team of sky lovers, we can all contribute to this effort and keep those charts, because the same area of Cygnus will be used for Globe at Night new moon in September as well. So you can use the same charts in September. Okay, onto those dates with asterisks. We start with pre-dawn tomorrow with the moon 2 days shy of new, and it's only 4.5 degrees northeast of Mercury. Now, Mercury is at magnitude 0, but its magnitude is reduced to 1.7 because we're looking through 14 air masses when the planet is this low. And here we see the simulated view through 10 by 50 binoculars at 4:45 in the morning. And I would recommend mounting those binos on the tripod if you can to study that thin sliver of the crescent moon. Remember, it's tipped our way for libration tomorrow morning. But whatever, give it up at 5:30 shortly before sunrise, because you don't want to have your binoculars aimed east when the sun comes up. Now, 4 days later in the evening, low in the west, Mars, Venus, and the young crescent moon form a 6-degree line as seen here through the same 10 by 50 binoculars. As Venus moves on its way towards greatest elongation east from the sun, which it will reach in October, it passes by Mars on the way and appears very close on 2 consecutive nights on the 12th and 13th. Hopefully, we get a clear night, one of those 2 nights, so that you can put your telescope on it and get a view of it like this. Here's a simulated mirror-flipped view of Venus and Mars through a Celestron C8 using a 26mm eyepiece. On July 24, Saturn, just a week shy of opposition, sits 9 degrees from the full moon, a very attractive visual pairing. 2 nights later, Jupiter, approaching its own opposition next month, sits 4 degrees north of the waning gibbous moon, as shown here in 10 by 50 binos. And last on our list of asterisks is 30 Pisceum, reappearing from lunar occultation around 3:18 in the morning on July 28th. 30 Pisceum shines at magnitude 4.37, which is fairly bright. That means you should be able to watch this event. Even from a suburban site, you really don't need a really dark location with a star this magnitude. So if you are out observing or imaging at 3 in the morning that morning, you can watch the star pop back into view from the moon's eastern limb around 3:18. I'd like to show you two adjacent targets on the moon to zoom in on and study. The targets are from the Explore the Moon telescope observing program. First is Mare Christium, the Sea of Crisis, a very flat mare that has a mass concentration located below its center. And maybe that's the leftover of the impactor, or maybe it's the result of heavy molten material rising up through the impact cracks to fill that basin. Now, when the sun angle is low on the date suggested here, you can look for shadows cast by undulations on the mare and the walls of craters that have impacted the mare since it formed. Macrobius crater lies just northwest of Mare Chryseum. It is 63 kilometers wide, and its western rim was punched by Macrobius C. The crater has terraced walls that are really still intact, and the central peaks, all of which stands out well in low-angle lighting on the suggested dates here. It's a very well-defined crater. Looks very fresh, crisp. It doesn't look to be worn by bombardment very much. Now we move on to the planets. Here are the inner solar system planets as of tonight, and I can draw a horizon line between Mercury and the Sun, suggesting that we can spot Mercury low in the east shortly before sunrise. And on the other side of the Sun, in the evening sky, Venus and Mars lie nearly on the same line of sight, so they should appear close together this month. As we saw, they do pass close by in the middle of the month. By August the 3rd, Mercury has raced behind the Sun. Venus has climbed a bit higher in our sky, drawing further away from the Sun, while our orbit, quicker than that of Mars, is slowly bringing the Sun between us. Now here's a second look at that Moon-Mercury pulse on the morning of July 8th. At 5 a.m., Mercury is 5.5 degrees above the horizon, so you will want a very unobscured view to the east, or maybe an elevated perch to see or photograph this pair. Mercury will shine at magnitude 0, but reduced to 1.16 by 9.4 air masses that we would be looking through at that elevation. Now, in theory, a Celestron C11 at 800x would show you Mercury's phase, which is 46% illuminated, but I don't think you can push an 11-inch to 800x. You would probably need a 16-inch monster scope to pull this off, and if you are so lucky, why not give it a try? Venus is now orbiting towards us as it comes around from behind the Sun, where it was back on March 26th. Throughout the summer and fall, as Venus circles around on its orbit, getting closer to us, its phase will shrink in terms of illumination, while its angular size will be increasing. In this graphic, we are able to detect its gibbous phase using a 10-inch dial, a short focal length eyepiece, and a 2x Barlow. A steady sky will be necessary to keep Venus still and show us its phase. You can try using a moon filter to reduce Venus's glare and maybe help you see the terminator. I've even stacked a -violet filter on top when observing Venus to remove some blue fringes from around it that's caused by our thick atmosphere when looking at objects quite low. Remember, Mars is not far from Venus this month, so if we swing that same telescope arrangement over to Mars, this is what we're going to see, just a red dot. It's too small to show any detail. Mars is about as far from us as it gets, and is as dim as it does get at magnitude 1.83. For detailed views of the planet, we're going to have to rely on images sent back from orbiters and rovers on its surface. That's because we'll have to wait over a year to begin seeing any details on that planet again. The next opposition is in December of 2022. Now here are the outer solar system planets, and the short green line next to the sun is our path for the month. And it's possible to draw a line that puts the sun on one side and Earth with the outer solar system planets on the other side. That means that when we turn our back to the sun this month at night, we should be able to find all of these planets at some time of the night. And in the case of Saturn, with Earth sitting between it and the sun by month's end, that puts Saturn in opposition. We'll be able to observe it throughout the night. Jupiter is rising shortly before midnight this week. It's in Aquarius, moving in retrograde as we pass by the planet on our inside orbit. By 1:15 in the morning, it has risen 20 degrees above the Merc. And that's a line I like to draw in the sky. I'd like to wait for a planet like Jupiter to get above that line before trying to see any detail on it. By the start of August, Jupiter will be rising at 9:30 in the evening, and it will transit around 2:45 in the morning, well before the start of twilight. So I would say that the prime time for observing Jupiter has begun. Here's a simulated view with a 10-inch dot and a 3.5mm eyepiece. And over the course of the month, Jupiter's brightness will increase by 10% as it gets closer to opposition, and its angular size will also grow by 5.6% this month. You can try using either a yellow-orange filter to help bring out some of the contrast in the cloud bands. And you would like to use a blue filter to help you see the great red spot, because its color will be greatly darkened as it passes through blue. And that'll help you find or enjoy seeing the great red spot in contrast to the lighter clouds around it. If you enjoy watching Jupiter's moon events like shadow transit and eclipses, we'll take a look on the night of Saturday, July 10. Actually, most of the action happens after midnight into the morning hours of Sunday the 11th. When Jupiter rises on the 10th, it's already going to have the Europa shadow transit underway, but it's going to be too low in the sky. You probably won't be able to see the shadow. But it will still be transiting 90 minutes later, by which time Jupiter will have climbed a lot, and you'll be able to see the shadow spot then. And while that's happening, Io is going to be moving behind Jupiter. But before it gets behind Jupiter, it's actually going to disappear into thin space as it enters Jupiter's shadow, which is off in this direction. So let me run this video for you, and you can see what I'm talking about. You'll notice that the great red spot rotates into view as Io disappears. So I think this might be a very fun project to try and make a still lapse, time lapse image or movie of this event. It would be an interesting attempt. Saturn is rising on or near sunset this month as it reaches opposition on August 2. It's in Capricornus, also moving in retrograde as we pass by the planet. And for pleasing details, I again suggest you wait for Saturn to climb above 20 degrees latitude, which it will reach by 3 in the morning at the start of this period, and by 1 in the morning when it's at opposition. Saturn transits on opposition night. It will be, when it does transit on opposition night, it'll be 28 degrees up in the south, and that's 3.5 degrees higher than last year's opposition in June. So we're going to be able to get finer details, I would imagine. Saturn and its rings will shine at magnitude 0.18 at opposition, but there is an effect known as opposition surge when the phase angle drops to perfectly 0. So if you're observing Saturn on opposition, it's possible it could be a little bit brighter than 0.18, at least briefly. And Saturn's largest moon, Titan, the only solar system moon with a thick atmosphere, that can be spotted in just about any optical gear, even binoculars. but you're going to need a 150 millimeter telescope, 6 inches or larger, to take in the smaller moons of Saturn. And you'll notice that Saturn's rings are no longer tipped to their max, hiding the southern limb of Saturn. Last year at opposition, the rings were tilted to their fullest and we couldn't see the southern limb, but now they're beginning to narrow. And they're going to continue narrowing for the next 4 years. The rings will appear edge-on and maybe impossible to see on March of 2025. A number 8 light yellow filter will help bring out Saturn's faint cloud bands and the polar regions. You might try a neodymium filter. It's going to block Saturn's prominent yellow butterscotch color, providing a different contrast to enhance the lighter cloud belts. Uranus rises after midnight this month. It's now shining around magnitude 5.8. Now, you young folk out there with fully dilated pupils observing from a dark site, well, you can see the planet with your eyes alone. I recommend you spot it first with binoculars. In binoculars, Uranus is going to be obvious. It's going to be the blue dot amongst all of the white stars. So you're not going to have any trouble identifying which dot is Uranus. Study it. Get to know the bright stars around it, then drop the binoculars down and find those same bright stars, and you'll have no difficulty seeing the blue dot of Uranus. I know that. I've done it myself. The last time I tried was 25 years ago, so I wonder if I can still do it. I'll try and give it a shot. Neptune is further east than Uranus, so it's crossing the sky ahead of it. It's over 20 degrees. Well, it doesn't really matter when it reaches 20 degrees because I'm not looking at it for detail. Telescopes under high magnification will bring out Neptune's tiny blue disk, and that'll help you pick it out from the field stars. Unfortunately, it's below naked eye visibility at 7.8. Now, if you would like to track asteroids, here are 2 that will pass through opposition this month: 12 Victoria at magnitude 8.8, and 6 Hebe, more than twice as bright, at magnitude 7.9. The red lines show their retrograde movements this month from east to west, left to right. By the way, asteroid 12 Victoria is featured on page 244 of this year's Observer Handbook with a detailed finder chart. Hebe passes within 5.5 arc seconds of an 8.25 magnitude star on Monday, July 26 at 1:21 in the morning. This close pass would also make for an interesting time-lapse movie if you're so inclined. There are 2 meteor showers this month, one peaking and one ramping up. The southern Delta Aquarids peak on July 28-29. Unfortunately, as the radiant rises, so does a fat gibbous moon right next door. So the SDAs will be largely wiped out by that bright moon. They do have a zenith hourly rate of 16 to 20, but I'm imagining that the moon's going to wash out all but the very brightest. Maybe some will hit our atmosphere around the zenith and give us a chance to see them far from the moon. Meanwhile, Earth begins to pass through the debris trail of Comet Swift-Tuttle in mid-July, and that signals the start of the Perseid meteors, which won't peak until mid-August, which next month's speaker will no doubt describe in detail for us. The stream gets thicker as the month wears on, so as the darker conditions return at the start of August, our chances of seeing Perseids are excellent. Deep space. Wow. There's so much to do or see, so little time. As I mentioned earlier, the dark night window is only 4 to 5 hours long this month, so it's easy to pull off an all-nighter, and you may have to, with so many deep space targets to choose from in and around the Milky Way. You'll easily run out of time first. Now, I'd like to zoom in on the area around Sagittarius. We are looking in the direction of our galaxy center marked with the +GC symbol. To me, the Sagittarius arm of the Milky Way looks like steam rising through the spout of the teapot. Now let's examine a Messier and NGC target in this area, starting with Messier 22. It's a globular cluster. It sits 2.3 degrees northeast of Cos Borealis, the star that's at the dome of the teapot. Just scan this area with binoculars or a spotting scope, and no doubt you're going to find it. It's also known as the Great Sagittarius Star Cluster in NGC 6656. It's one of the brightest and largest that we can see from the northern hemisphere, because at 10.6 thousand kilometers away, it's the second closest of all globulars. Only Messier 4 is closer. Other globulars can be up to 3 times this distance. M22's angular size is 32 arc minutes, making it appear as wide as a full moon. And it's a fine target for stabilized binoculars or a telescope at low power. It has a combined mass of 500,000 suns and is 12 billion years old, which makes it around 88% as old as the universe. 2 black holes in the cluster were detected by the Very Large Array Telescope in New Mexico, as reported in Nature in 2012, and I've read that dozens more are expected to be inside that cluster. Our next target is from the finest NGC observing list, NGC 6369, also known as the Little Ghost. It is a planetary nebula, the expanding shell of a sun-like star at the end of its life. It's found a half degree west of 51 Ophiuchi at magnitude 4.7, so it should be very easy to locate. The Little Ghost Nebula is the expanding shell of a dead star's atmosphere, as I mentioned. It's glowing because of emissions that were created by strong ultraviolet radiation from the exposed core of the now dead star. That's where the fusion had occurred during the star's lifetime. An ultra-high contrast filter allows the wavelengths of the nebula's emissions from ionized oxygen and hydrogen to pass through while blocking sky glow and light pollution, making it much easier to spot the ghost. You will want to have a light pollution filter in your inventory to help you see not only this, but other planetary nebulae. Now, heading north along the Milky Way up to the constellation Scutum, we can check out another Messier object and a double star involving a red giant right next door. Open cluster M11 sits just a little under 2 degrees southeast of Beta Scuti, magnitude 4. The double star, noted here as H650 in this insert, it lies about 3/4 of the way to the cluster. Messier 11 is one of the densest open clusters, with close to 3,000 stars packed in an area 20 light years wide. Now, most of the open clusters we look at, they may have a few dozen stars, maybe a few hundred, but 3,000 stars in a cluster is very impressive. And this cluster is only 220 million years old. Its hottest members are massive Class B stars and some red giants who have already exhausted their fuel and have expanded into the red giant phase. The cluster is bright enough to be noticed as a bright concentration by eye alone under dark skies. It shows up well in binoculars, and in telescopes, it stands out as a rich concentration against the backdrop of the Milky Way. After checking out the Wild Duck cluster, slew a half degree northwest to find the sixth magnitude's orange star, HR 7083. It is a K2 giant star off the main sequence. The Hipparcos survey says it's 1,744 light years away, so that's a very bright star to be shining at magnitude 6 from 1,700 light years away. This star is part of a triple star system, though component B, the closest companion to the 6th magnitude A component, is dim at only 12 magnitude, and it's going to be difficult to find it in the glow of the main star. The more visible component C is brighter at magnitude 8 and at a more comfortable separation of just under 2 arc minutes. The Stellarium picture here shows a low-powered view through an 80mm refractor. HR 7083 and its C component are the two bright stars in the center. And with a 1.5 degree field of view, you can still see the Wild Duck cluster down in the southeast. For our final trio of targets, we'll travel further up the Milky Way to Cygnus, gliding near the zenith. And that's where we will check out two more open clusters and a double star. Open cluster M29 is easy to find under 2 degrees south of Gamma Cygni. M29 is an extremely young cluster of stars, just 10 million years old. The cluster's 5 most brilliant stars are supermassive B0 stars, 17 times more massive than our sun, and wait for it, 160,000 times more luminous. That's bright. Stars this massive live for only 10 million years, putting an upper limit on this cluster's age. And as a cluster, its apparent magnitude is 6.6, but I've read that it would appear an amazing 1,000 times brighter, if not for extinction caused by leftover material from the cluster's Earth cloud and more dust in the Milky Way arms. The cluster's brightest stars will form for you either a square and triangle or a stubby bent-handled dipper or the hyperbolic shape of a cooling tower. NGC 6819 is found 5 degrees south of Delta Cygni. Under modest magnification, the rich cluster reveals a V-shaped concentration of bright stars, and that suggests a fox head, hence the name. It's unusually old for an open cluster at 2 billion years old, which is about half the age of our solar system. Other clusters usually don't last this long. They are taken apart, the member stars drift apart due to gravitational interaction with other stars or because of drag from dust and gas that the clusters will pass through. Those will tend to pull the stars apart and break up the cluster. So this cluster must be in a relatively clear region of the Milky Way to have hung together for so long. Our final target is HR 7529, a magnitude 5.9 star found a little less than 2.5 degrees northwest of Eta Cygni. It is a member of a multiple star system. The Washington Double Star Catalog lists 6 companion stars. Now, the star and its nearest companion are the easiest two to find. The primary A shines at magnitude 6.4, and its neighbor B holds its own at magnitude 7. Component F is the next easiest at 2 minutes and 20 seconds to the southwest, magnitude 922. And with high magnification, a nice dark sight, and steady seeing, you might be able to spot components C and D. They are faint at magnitude 12. And with that, I will end my presentation and try to answer any questions.
All right, thank you so much, Arnold. That was a very comprehensive sky this month. Thanks so much for putting it together for us. I know it's very time consuming, especially when I have to review all of the upcoming events. Emma, do we have any questions for Arnold?
We do have a couple of questions. First off, Lewis would like to know, would using thorium require much water in a reactor, and how would this affect the limited water supply on the moon?
Well, I'm afraid I have not researched details such as that, so I'm afraid I'm not really qualified to answer that. I'm sorry.
Okay. Second question is, how much does the size of Mars change from our point of view, from its closest point to us to its furthest point in its orbit?
Well, I may not have those numbers right in front of me, but what I do know, and I can probably scare them up if I play with Stellarium, and I can do that and type the answer into our chat window. But what I do know off the top of my head is no other planet changes in apparent size as much as Mars does. It's a very small planet to begin with, half the size of Earth. And when we are on opposite sides of the sun, or getting near it, it's the size it is in this presentation that I showed you just now. And I can maybe scoot back to that slide and find it. Let me just hit there. There we go. Saturn, outer solar system, Mars. There we are. So it's as far from us as it gets. I don't have that number on this slide. Oh, here we go. Angular size, 3.8. That's as small as it will appear. And how large it appears, well, that depends on how favorable the opposition is. It varies greatly because Mars has a highly elliptical orbit, and when we pass between it and the sun, Mars could be farther away or closer to us, depending on where it is in its orbit. The closest it ever did come was, I believe, in 2003. That was the year when Mars got really, really close. So what I'm going to do is find out how large it looked at that point, and I'll type it into the chat window.
Thank you very much. That's all the questions.
All right. Well, thank you.
Good. Thank you, Emma, and thank you, Arnold. Let's move on to our next speaker, John Percy from the University of Toronto. He'll talk to us about variable stars.
Okay, you can all see, you can all hear. Okay, thank you very much. As some of you know, variable stars are the main interest that I've had in astronomy for something like 60 years. And it seemed to me that for a group of recreational astronomers, it would be appropriate to just remind you of how interesting and exciting variable stars are, and how easy it is for you to observe them either for fun or to actually do real science. So I want to show you just a few examples of variable stars that are interesting for different reasons, and hoping that you will go out and actually observe these. And I just remembered I was supposed to tell you where I was. I'm in West Toronto under fairly muggy skies here. So here's an outline of some of the reasons and some of the things that I'm going to mention. A lot of the stars that you know and love turn out to be variable in brightness. This is part of their personality. It's also part of their physical behavior. A lot of these stars have interesting human interest stories behind them. And one of the reasons that I like astronomy is the human interest aspect of it. Astronomy isn't just done by textbooks or machines, it's done by real people. And of course, you can go out and observe variable stars for fun, for recreation, or even more remarkably, you can actually go out and observe variable stars to contribute to astronomical research. And I've been working for many, many years with skilled amateur astronomers, helping their observations to see the light of day and to contribute to science. And finally, variable stars are still on the frontiers of astronomy today, and I'm going to mention a few examples of that. Now, I'll flash this slide up at the end as well, but I just want to assure you that there's lots of resources to help you do this. The absolute best place to go for information about variable stars for people like you is the American Association of Variable Star Observers, which has existed for well over 100 years and is based in Cambridge, Massachusetts. Another thing that's very easy for you to refer to is the RASC Observer's Handbook. And there are several pages in the handbook which will provide you with a beginning of variable stars, simple charts to make observations, an explanation as to what kinds of variable stars there are, and one or two features on specific stars. Now, I can modestly say that the best place to go for a book, even though it's slightly out of date, is my book, Understanding Variable Stars, published by Cambridge University Press. You should be able to find it out there somewhere. It's available as an ebook as well as a hard copy. And finally, you may have noticed that in every issue of our journal, I have a column on something that interests me. And I've referred here to a recent column called Variable Stars I Have Known, and you should too. So do go to that article there. I'll mention some of the stars in this presentation, but there's a few others there that I can highly recommend. So let's start with the best known star in the night sky, at least for northern observers, and that's Polaris. But Polaris is more than just a star in the sky that happens to help us to find north or to find our latitude, but it isn't the brightest. One of the things that I give lectures on is misconceptions in astronomy. One of the great misconceptions is that Polaris is the brightest star in the night sky. Actually, it ranks number 47. But it's a triple star. The brightest star in the system is a white supergiant star, and it's a 3.969-day Cepheid pulsating variable star. And the graph at the bottom here shows the brightness of the star measured in magnitudes. This shows that the amount of variation is a huge 2%. So I don't advise you to go out and try and measure the variability of Polaris, particularly with your naked eye. It's hard enough to do with photoelectric photometry. But it's an extremely interesting star. One of the things that we can do with it, and this is one of the important tools of variable star astronomers, is something called O-C. Now, O is just the observed time of the maximum brightness of a variable star, such as Polaris, and C is the calculated time, assuming that we know the period and the period is constant. So we can calculate when the star should be at maximum, and we can calculate O-C. Now, if the star's period was constant, then O-C would always be 0, and we just get a straight line on this graph that you see here. But no, the graph is not a straight line. Indeed, it's very close to being a parabola. And a parabola occurs if the period of the star is slowly increasing. And the period increase can be very slow because the observed effects are cumulative. It's very much like having an error on your watch. It may only be a second a day, but after a few weeks or a few months, you can clearly tell that there's something wrong with your watch. So in the case of Polaris, the period is increasing by 4.5 seconds a day, seconds a year, sorry, and that is almost certainly due to the evolution of the star. The star is slowly getting larger. Larger objects vibrate more slowly. They have a longer period. And so we can actually observe this and test our models of stellar evolution. And we can do this for many other kinds of variable stars. But another remarkable thing about Polaris, and this is almost the only star that this occurred in, is that over the last century, the amplitude of variation has slowly decreased. So in this graph at the top here, that's the amount of variation in percent, decreasing from 10%, apparently on its way to 0 by the year 2000. Now, in fact, it didn't decrease to 0. It remained at 2 or 3%, as you can see from the rightmost points on this graph here. And this phenomenon was discovered by a graduate student, Armando Arellano, when he was a student working at the University of Toronto using the David Dunlap Observatory in Richmond Hill. Now he's one of Mexico's most distinguished astronomers, and we're very proud that he obtained his training here at the University of Toronto. So this is remarkable. We really haven't a good explanation as to why Polaris has done this. So it does have the potential of telling us something new about stellar physics. Now, the other reason that Polaris is extremely important is that it's an anchor for what we call the Leavitt Law. The Leavitt Law used to be called the period luminosity relation for Cepheid pulsating variable stars. And it was discovered by Henrietta Leavitt at the Harvard College Observatory. And she noticed that in the Magellanic Clouds, which are stars all at the same distance, the ones that had the shortest periods were less luminous. The ones that had the longest periods were more luminous. And so the graph on the right here shows that relation. And it can be calibrated if you know the periods and the luminosities of a few Cepheids. And in particular, if there's Cepheids that are near enough so that you can use the parallax method in order to determine their distance. And so because Polaris is so close, you would have thought that it was a very good candidate for calibrating this law. But strangely enough, until only a few years ago, the distance of Polaris was quite uncertain. There were some astronomers who thought it was about 330 parsecs, others who thought it was more like 440. And now we know through the Gaia satellite that the distance is the latter. It's 445 parsecs. And so this allows us to confidently use Polaris as an anchor for this very important relation. Because using the period luminosity relation, if you observe a very distant Cepheid but can measure its period, then you can assume its luminosity and from its apparent brightness, use the inverse square law of distance to determine what its distance is. And this is one of the cornerstones of modern cosmology. Well, I mentioned that Polaris was not a very good star for you to start observing. One of the best ones, if not the best one, is Delta Cephei, which is the Cepheid variable that actually gave these stars their name. So here we see a photograph of the little corner of the constellation Cepheus, which, as you know, looks like a house. And there's this little triangle of 3 stars in the corner of it, Zeta at 3.6 and Epsilon at 4.2. And your job is to estimate what's the brightness of Delta in the upper left here relative to Zeta and Epsilon, whose magnitudes are known and are given on this chart here. Now, what people tend to ask at this point is, well, what's the answer supposed to be? I have to point out that, well, that's for you to figure out. This is science. You're making a real observation. So do go out with a star like this and get started. Now, you might wonder if I actually went out and made these measurements and submitted them to the AVSO, then what use would be made of them? And I'm just taking one example here from my latest column in the RASC journal, which is on the death of the sun. And the previous presentation mentioned the case of planetary nebulae, which represent what happens after the sun casts off its outer layers and turns into a white dwarf. Well, when the sun undergoes this transformation, its size is decreasing, so its period should be decreasing. And so the star AV Cygni, and that's a typical variable star name, has been observed for almost a century by the AVSO, and we can use a technique called Wavelet Analysis, which actually fits a sine curve to the different parts of the light curve, the graph of brightness versus time, and estimates at each point what the best period is. And that's what's shown in the red curve on this graph here. And the black line is a linear fit to that curve there. And it shows that the period of AV Cygni is slowly decreasing. And over the course of a few thousand years, perhaps represents the fact that AV Cygni is transforming from yellow giant star, which it is now, to a white dwarf and a planetary nebula. So this curve here is based on thousands and thousands of visual measurements made by skilled amateur astronomers through the AVSO. And this is one of the kinds of science we do. This was a project done by a fourth-year student working with me last year through our work study program. And we've just posted this as a paper, and we will probably submit it to the journal of the AVSO, which is how we try and feed back this sort of work to the observers who actually make the observations. Now, you've probably heard a little bit about Betelgeuse recently and its so-called great dimming. which is shown at the end of this graph here. This is a graph of the magnitude versus Julian date. And these are all photoelectric observations here. Now, the claim really is that there's something strangely unusual about the dimming of Betelgeuse. But actually, when we take a century of observations, visual observations, photoelectric observations, what we learn from this is that Betelgeuse varies on two time scales, 390 days and about 2,000 days. And both of these variations have variable amplitudes. And it turns out that at the time of the Great Dimming, a year or so ago, both of those variations were at the minimum in their cycles, and both of them had their amplitudes at the maximum. And so adding these two things together produced this unusual fading of this star here. But the point here is that if you want to understand what a star is doing, it's often useful to look at the history of this star. And so what I've told you here is based on a century of observations by skilled amateur astronomers for the AVSO. And from that, we can deduce what the different timescales and behaviors of Betelgeuse is. Here's another good star to start observing, Algol. There's a chart of Algol in the Observer's Handbook, and it's an eclipsing variable star. And for a few hours, it fades quite noticeably. So one observation that everybody can do is go out, look at the constellation Perseus, and simply ask, well, is Algol at minimum or is it at normal brightness, where it's about the same brightness as the other stars in the constellation? Remarkably, it turns out that Algol and its period were apparently known to the Egyptians 3,000 or 4,000 years ago. A paper got submitted to the Astrophysical Journal, and I was asked to see if I could recommend someone to try and referee this paper because the claims seemed to be quite remarkable. But when it was carefully reviewed, refereed by expert astronomers, they actually believed that for whatever reason, the ancient Egyptians observed Algol and observed its eclipses. The fact that its name means ghoul or the demon star or something like that also suggests that Islamic astronomers knew about its eclipses too. But at least in modern times, John Goodricke is given the credit for suggesting that the variability might be due to eclipses. He also was the one who discovered the variability of Delta Cephei. And remarkably, he did all these things in his tragically short life of only 21 years. But at least by the time he died, he was a fellow of the Royal Society. So he was recognized, and he was an amateur astronomer. He and his next door neighbor, Pigott, did a lot of interesting things in terms of the beginnings of variable star astronomy. Now here's another star whose chart is in the Observer's Handbook here. This is Mira in the constellation Cetus. It's the prototype of pulsating red giants. And it's interesting that its variability was actually discovered in 1596, which means that its variability was discovered before Galileo's important work providing a proof for the Copernican hypothesis for how the solar system was laid out. And of course, the two supernovae discovered by Tycho in 1577, the one discovered by Kepler in 1604, these also predate most of Galileo's work. And they suggested that despite what Aristotle said, the stars were not always perfect, not always unchangeable. And so in this sense, the stars helped to overthrow the Earth-centered model of the universe. It was not just solar system phenomena that supported Copernicus and overthrew the Ptolemaic system. Okay, quickly a few frontiers of how variable stars figure in modern astronomy. You've probably heard of pulsars. They're rapidly spinning neutron stars being formed in the collapse of massive stars at the end of their lives. And in this set of images here, we see how the how the brightness of the pulsar, which is this star here towards the very center, varies over the course of the variation, which is only 1/30th of a second. The Crab pulsar pulses 30 times every second. Now, one interesting thing is that apparently the human eye can see this flickering in a sufficiently large telescope under sufficiently good conditions. And I've wondered perhaps whether the DDO 74-inch is large enough where you might be able to see this on a reasonably clear night, or whether our skies are simply too bad to observe something like this. By the way, if you want to get involved in this, the AAVSO has a high energy section, and they make observations that are relevant to things like neutron stars, black holes, white dwarfs, and other high energy phenomena in astrophysics. I mentioned supernovae. Supernovae are still very, very important in modern astronomy. I hope you've all heard of supernova 1987A, discovered independently by our own Ian Shelton at the top here, but also by amateur astronomer Albert Jones, probably the most remarkable variable star observer ever. He's made over 500,000. He made over 500,000 measurements during his lifetime and was referred to as the man with photoelectric eyes. So here's an example of a light curve here of a supernova. These observations coming from skilled amateur astronomers. Amateur astronomers discover supernovae as well as measuring them. And supernovae are now one of the other keys to the cosmic distance scale, along with the Cepheid pulsating variable stars, because their peak luminosity is very close to being constant. And so we can use them as lighthouses, as it were, for very distant objects. Certainly one of the great frontiers is exoplanets. One of the remarkable things, I think, is that the nearest other star to the sun, which is Proxima Centauri, not only has exoplanets, but one of them is Earth-like in the sense that the temperature would allow water to exist as a liquid, which is probably a prerequisite for life. Now, unfortunately, particularly Earth-like exoplanets, if they transit across the face of their star, produce only a slight dimming. So here's a graph here showing the dimming of this star because of its exoplanet, and it's only about 0.005 magnitude. So it's about 0.5%. But amateur astronomers can contribute to exoplanet research. The AAVSO has an exoplanet section. So if you go to this address here, you can find out how you, with a CCD camera, can contribute to modern research on exoplanets. I want to finish up with a couple of examples of some recent work that's been done by my colleagues. And this is Maria Drought. She's actually my next door neighbor in the Astro building at U of T here. And she was of note because she led the team which produced really the birth of multi-messenger astronomy. Now, you may have heard of multi-wavelength astronomy, where you look at cosmic objects at different wavelengths, from radio to X-ray to gamma rays, and with all the ones in between. And that's been done for many decades. Multi-messenger astronomy now occurs when we can obtain signals from gravitational wave bursts. And a gravitational wave burst was observed 2 or 3 years ago. Previous to that time, gravitational waves bursts could not be localized because there were only 2 active observatories, and that was insufficient to triangulate. But when a third and to some extent a fourth gravitational wave observatory were able to measure the burst, it was possible to approximately localize this burst. And so Maria and other teams went out looking for it, and indeed her team won. At the bottom here, you see this very faint object here, which is coincident with the burst. And it turns out to be the in-spiral and merger of 2 neutron stars. producing a huge burst of gravitational waves when they merge together. Now, it turns out that this phenomenon is very important because it seems that this is how most of the elements in the universe heavier than iron are formed. It was previously thought that they were all formed in supernova explosions, but this is not only an important development in instrumentation and observation, but also in our understanding of a fundamental part of astrophysics. So again, there's a link here to the press story. And finally, and this is even more recent here, in one of my columns last year, I talked about Assassin, which is what we call the all-sky automated survey for supernovae, ASAS-SN. And this is a huge database. It has huge amounts of information in it. In fact, this is one of the databases that my students are now using to study variable stars, because there's of the order of 2,000 days of intense observations of something like 500,000 variable stars. Now, Anna O'Grady, who is one of our graduate students, was actually looking, data mining the Assassin database for strange objects called Thorne-Ditkov objects, which are hypothetical red giants which have acquired a neutron star core. She didn't definitely find any of those, but what she did find was a whole new population of stars called superasymptotic giant branch stars. So these are stars that are even more luminous than red giants being the phase that the sun will go through and towards the very end of its life. So again, there's a link here to a press story here. And if you want to do some of this kind of stuff yourself, there's actually one of the Zooniverse projects for you to work on. I hope you're all familiar with Zooniverse. It sort of started with the Galaxy Zoo project, in which you were to classify images of galaxies. Well, in this case, the Assassin team has called on your help in classifying some of these 500,000 variable stars from their light curves. And I might point out that one of my students last year has found out that, at least for pulsating red giants, about two-thirds of all the Assassin classifications and analyses are incorrect. So there's actually a huge amount of work done here. So if you see that, if you refer to that JRAS column that I mentioned on the previous slide there, it has some ideas and the appropriate web links if you want to decide on cloudy nights to do data analysis and data mining from the Assassin database or from the AVSO database or whatever. There's very good software available, a package called VStar, which is what my students use for this, for doing analyses of this kind. So I'll end simply by putting up this list of resources here that reminds you that if you're interested in variable stars and want to start observing them, there's lots of places that you can go for information. So thank you very much. If you got some questions, I'd be happy to try and answer them. Thank you.
Thank you very much, John. Always a pleasure to have you present to us. Let's go to Emma. Do we have any questions for John?
We do. The first question comes in from Lewis. Is Betelgeuse really a variable star?
It is a very variable star, yes. There's absolutely no question that Betelgeuse is a variable star. This is its light curve. It varies by something like 1.5 magnitudes and in a very complicated way. No question that it's variable.
Thank you. Question 2 also comes in from Lewis. Can our sun be classified as a variable star because of changes that occur in its activity, especially as related to flare activity?
Definitely so. The sun is a variable star in several different ways. If you remember the previous presentation, the images of the sun with sunspots, as sunspots rotate around the sun, then the sun varies slightly in brightness with the same period as it rotates, which is about 30 days roughly. It also varies, as you mentioned, because it flares. It could be observed as a star with exoplanets. Many of you have observed the transit of Venus and transits of Mercury. You know that when a planet transits across the disk of the sun, its brightness presumably decreases by 1% or so. And so it's variable in that way. And it also is a very low level pulsating star in a very complex sort of way. So it's 4 different kinds of variable stars.
Thank you. Andy wants to know, with sky surveys doing a lot of the data gathering, what are the best types of variables for amateurs to observe?
I could say that almost any kind of variable star is still worthy of observation. And the good thing about having the AAVSO is that with its team of scientific advisors, it can suggest specific projects on specific kinds of variable stars that you can do. So I, for instance, am one of the scientific advisors for the long period variable section, which observes things like Mira stars, but there's the exoplanet section, the high energy section, there's a solar section, et cetera, et cetera. And so they can recommend the kind of measurements that are particularly useful. And then there's all this data mining stuff. There's all this stuff in these databases here, which is either incompletely analyzed or the analyses are incomplete or incorrect, as I and my student found them to be for the red giant stars. So there's still lots to be done.
That's all of our questions. Thank you.
Oh, thank you. And by the way, this is my 60th year of Toronto Centre membership, so I'm very pleased to be with you tonight.
Very good. How many years, John?
60.
60.
I joined in 1961.
Wow. I thought I heard 60. I just want to make sure. That's an awful long time. Congrats.
I have a column coming up in the journal on that.
Fantastic. Thanks again for your presentation, John.
My pleasure.
Let's move on to our next speaker, Trevor Jones from astrobackyard.com, and he'll talk to us about deep sky astrophotography, proven methods for better images.
Hi, everyone. My name is Trevor Jones, and I am coming to you from St. Catharines, so just south of the lake from a lot of you in Toronto. And yeah, deep sky astrophotography is something that came into my life about just over 10 years ago now. And it really was life-changing. Unlike the previous speaker, my background wasn't in science, but art. I went to art school, and you know, photography and visual art was a big part of my life and a big part of my career before I actually entered the world of astrophotography. So knowing that this is the RASC Toronto crowd, I'm assuming that a lot of you are shooting in light polluted skies, just like I am here in St. Catharines. So I'll try to focus on deep sky astrophotography, or deep space of nebulae and galaxies from a light polluted area, because astrophotography is a very broad subject that covers, you know, a lot of areas, but we'll focus on deep sky astrophotography through a telescope from the city. So just a little bit about me. Again, my name is Trevor Jones, and Astro Backyard is kind of the brand that surrounds everything that I do. So astrobackyard.com is a website where I blog my adventures in the backyard photographing deep sky objects, tips and tutorials. And then I also have a YouTube channel where I share a lot of the content from my nights in the backyard shooting various deep sky objects. So the website and YouTube channel were started in 2015. As of 2019, it became my full-time job. And then I've done some really cool things. I was fortunate enough to be the instructor for Canadian Astrophotography School in 2019. And I even got my first NASA astronomy picture of the day last year. So it's been a wild ride, but this addictive, rewarding hobby of astrophotography is what has led me down this path. And I think that people that are, have sunk their teeth into astrophotography or even just getting started will quickly realize how addictive it is, and it really is. It can really change your life in a positive way. So I'm a die-hard astrophotographer, and I guess I would have to be to continue to be so passionate about photographing the night sky from the city with the weather that we have here in Southern Ontario. It's unpredictable, and it's obviously very cold in the winter, not very pleasant to be outside on some of those nights. But the toughest part really is, waiting for a clear night in the anticipation of your next deep sky project. So as I said, nebulae and galaxies and even sometimes star clusters, deep sky objects are my passion. But I've also started to explore planetary photography as well, photographing planets. You can see the planet Saturn and Mars. That was nearing opposition last year. So there's so much to explore. Obviously, the night sky is just full of wonder, and it really is a hobby that can, expand and grow over time, and it's just endless. So I base my entire life and my schedule around a clear forecast, which we haven't had in a while. But it really is, there's a lot of sacrifice and commitment if you're going to go this hard into something as I do with astrophotography. So those pictures there, you can see my little refractor telescope on an equatorial tracking mount with a dedicated astronomy camera attached on the top there. And then below that is one of my larger telescopes, the largest, an 11-inch Celestron SCT. And so that's my planetary telescope. It has much longer focal length and magnification for objects like that. Now, I was asked to make sure that this was a little more intermediate to advanced in terms of the presentation format for this. So forgive me if I'm going too fast on some of these astrophotography terms and equipment, but I'll leave time for questions at the end, and hopefully you'll have a few of those. So my primary imaging location is, of course, the backyard. So I'm in the north end of St. Catharines. It's a Bortle scale class 7. It's actually gone up a class recently in the last 5 years with the introduction of the really bright LED street lamps that are, all the way down the street. So it's a very bright area. There's a shopping plaza close to me, and probably similar to a lot of the neighborhoods around the GTA. So you would think that St. Catharines would be a little darker, but I'm quite sure that my skies are similar to GTA skies. But that being said, I'm lucky enough to have good views to the north, east, and south, which is great for astrophotography in the way, the apparent rotation of the night sky goes. In the west, I do have a mature walnut tree, so objects tend to run into that eventually when I'm photographing them. You can see it without its leaves in the top picture there, but of course that really fills out in the summer. So my backyard bounty, these are some of the better images I've managed to take from my light polluted backyard. And, when I started this hobby, I really didn't think it was possible to take great deep sky images from the city, from a light polluted area. But over time, I've discovered that just isn't true. And it just takes the right approach, and you do have to work a little bit harder. Usually what I mean by working a little bit harder is soaking in more exposure time on a lot of these targets to overcome the drawbacks of a washed out city sky. So these are varying objects here. You can see the Whirlpool Galaxy, which is on the smaller side there in broadband RGB true color. The Bubble Nebula, which is quite a larger object, but we're kind of zoomed in there, and that was shot using narrowband filters. The Veil Nebula next to that was shot with a color camera and a multi-bandpass narrowband filter that kind of separates the important wavelengths of light that you want to collect for an image like that. And then the Trifid Nebula is, I surprised myself on that one. That is a broadband true color image with no filter using a DSLR camera from the city. So, you really have to work at it on the processing side of things to create an image like that from a light polluted area. But I just wanted to throw that in there so you know it is possible to take images like that. So I like to think of it as smart imaging. So a successful deep sky astrophoto is the result of planning, smart acquisition, and careful processing, as I mentioned. So when I say planning, I mean the right subject for your equipment, your imaging conditions, and the moon phase. It's not like I can say, okay, it's supposed to be clear on Friday. I've always wanted to shoot the Lagoon Nebula, so that's what I'm going to shoot. You really have to check to see if the type of object is a good fit for your equipment and your conditions in the moon phase before you start shooting. So it really limits what's available to you. The acquisition stage, the collecting of the pictures, it requires the right approach to the exposure lengths, the filtering that you use, and the timing, of course. Like I said, when and where is this object going to be? And then the image processing, the parts that are especially important when it comes to photographing deep sky objects from a light polluted area, the gradient extraction is huge. If you're lucky enough to photograph the night sky, whether it's wide angle, wide field through a telescope, or a lens from a dark area, unlight polluted skies, it's so much easier to process because you're not spending half the time or 75% of the processing time just reducing that glow of the sky and creating contrast between the object you're photographing and the sky itself. Selective stretching is another key aspect of careful image processing. I'll get to that in detail in a minute. So here's an example image. I like to call it what went right. Because this image to me did go right, and actually I have a print of this on the wall opposite me right now. I was so happy with it. So what went right with this photo was that so the target location for the time of year, this is the Seagull Nebula. So in February when this was shot, this object was rising in the southeast from my yard, and I was able to collect plenty of images on this target, enough to create an image with a healthy signal to noise ratio and actually do it justice in the processing. If you're not familiar with the signal to noise ratio, all that refers to as the amount of signal or the light that your camera can collect versus the noise, which is just the artifacts and the result of a digital camera sensor through these long exposure photographs. So the signal to noise ratio is big, and you overcome that with more integration, more images. So this nebula also was a great choice to shoot using the filters that I did, which were hydrogen alpha, O3, and S2, sulfur and oxygen. So it's the right type of object for the filters I was using. The object was the right size for the telescope, the image scale, and the camera sensor. And it just turned out right because I did this planning beforehand. So this is an example of when everything comes together in the amazing images you can collect from the city. So before you start a new project, you need to ask yourself a few questions. Is it possible to image this object from the city successfully? Like I said, a Milky Way wide angle photo or a faint reflection nebula, those are nearly impossible to shoot from a light polluted sky. You need to travel somewhere dark to get those dim objects, and particularly in that blue spectrum of the reflection nebulae and the dim dust. That's very hard to do from the city. How much exposure time will I need to actually create an image that's worth processing? Does it need multiple nights of image collection, say 10 plus hours of integration for a strong image? And what can I actually collect from my backyard? That example you see on the right there of the Veil Nebula, that's actually the flying bat section of the Veil Nebula, Eastern Veil Nebula. That's a great example of what is a great choice from a light polluted backyard, because it is that supernova remnant that's just absolutely glowing in hydrogen alpha and the oxygen 3 wavelengths of the spectrum. using a multi-bandpass filter that isolates those two band passes, you can just capture a really striking high contrast image using a one-shot color camera, whether it's a dedicated astronomy camera like the QHY268C used, or a DSLR mirrorless camera. So that's a great target to shoot from the city. You expect to get good results with that, as opposed to something like a reflection nebulae, which is much tougher from a light polluted area. So for the planning itself, I like to use this. I already heard someone bring it up, Stellarium. It sounds like it's a pretty household name for this crew. I use it all the time. It's so handy. And I use it for planning my projects. I look ahead months in advance to see where objects are going to be in the night sky, where the moon is going to be, and really helpful to actually load in a custom landscape of your actual backyard. So that's my actual backyard horizon you're seeing there, where my neighbor's garage is, where those cedars point through, so I can see when when the Lagoon Nebula is going to be hidden by a tree for 10 minutes. It's really handy for planning, and the process involves taking a panoramic image of your backyard and loading it into the software. And I can point you in the right direction of a tutorial how to do that for anyone interested. And then there's the sensor view, which you can see on the top there, where you're actually plugging in the details of the size of your camera sensor and the focal length of your telescope to see the projected size of the deep sky object you wish to shoot. So that's really handy too for framing. You can get an idea of, okay, is my gear a good fit for this target? Is it going to be too small, too big? So Stellarium's a great tool to use for the planning stage. And lastly, in terms of planning, you need to see, okay, well, how long will this object be in my night sky before it hits, in my case, the walnut tree to the west? So can I get 3 hours of exposure time on it? Is it only 2 hours because it's so low? So that's why it's really handy to get in that custom landscape, because it may be available for 6 hours for some people and only 2 hours for you because you've got trees or other obstructions there. So that's really handy in the planning stage. As I brushed on earlier, multi-bandpass filters, multi-bandpass narrowband filters, they haven't been around for too long, but they've changed the game. I hate to use that cliche, but they really have. So if you're using one of these filters with a color camera, it will literally block out nearly all sources of light other than those specific band passes associated with the light that you want. So it's usually, a lot of these deep sky objects and nebulae have a strong hydrogen alpha signal. So we can isolate that, but on top of that, also a slight oxygen 3 signal too. That's glowing in a lot of these deep sky objects as well. So doing them both at the same time through a color camera has pretty astonishing results. Here's a couple example images shot with multi-bandpass narrowband filters. The Helix Nebula is one I'm particularly proud of because it was an iconic image of space I saw early on that I never thought I'd be able to photograph myself, especially from home. And that was using an Optolong L Extreme filter, just so a dual bandpass, O3HA. And then the Elephant's Trunk Nebula on the right was with a quad bandpass filter. This one is largely, again, hydrogen alpha and oxygen 3, but also a slight bandpass in H beta and S2 as well. Very subtle, but it gives you plenty of options and really fun data to play with in the image processing stages. So if you do want to shoot broadband images, which is just true color images in the broad spectrum of light without any of those harsh filters, it is possible, but you're going to want to shoot during the new moon phase and the weeks surrounding the new moon phase, just to give yourself the best chance possible. Also, if the object's higher in the sky and not low on the horizon close to the light dome, that will help as well. But really, the biggest thing when it comes to shooting these full color RGB images with a one-shot color camera or DSLR, it really comes down to the processing. You'll really have to work at it, and it's largely that gradient extraction stage of removing the light pollution from the image and just digging out those precious details underneath. If I'm working on a particular broadband true color project, I'll go to the lengths of renting an Airbnb at a dark sky location just to collect precious broadband data from a dark sky area, just even for one night to add to an existing project. So image processing itself is, quite magic when you look at the before and after of an image like this. Funny enough, for this image, it really wasn't even a clear night. There was a poor transparency, which you can see by the two bright stars in the processed image on the right. They're so fuzzy because they're just looking through a thin layer of clouds, essentially. But it's remarkable, the image lying underneath the light pollution, and how we can actually bring out the color and the details and the amazing structure hidden beneath a washed out city sky. So that is the Jellyfish Nebula in Auriga there. So image processing tools that you'd want to use, these are the ones that I use for registration, integration, and calibration. Very important. You're basically loading in all the images you've collected. I like to use Deep Sky Stacker. It's a free tool that still works great. The registration, you can think of it as just aligning all the images you've taken together and combining them. And then the calibration is using calibration files like dark frames and flat frames to help calibrate the image and produce a solid intermediate level file to process further. Sequator is another great free tool that works well. Adobe Photoshop is where I do the majority of my image processing, and that's largely due to personal taste. I've been using Adobe Photoshop for over 20 years, thanks to that photography and artistic background. Other people like to use PixInsight start to finish for their image processing, and it was designed specifically for astrophotography. So it has some really powerful specific tools that you can tap into for PixInsight. But the reality is a balanced approach between those two software tools is probably your best bet. There's some additional third-party tools. Topaz Labs Denoise AI is a powerful noise reduction tool that you'll want to use carefully. The Astronomy Tools Action Set is a plugin for Photoshop that I recommend. And then StarNet++ is a script essentially that removes the stars from your image. I like to say separates the stars from your image because most of the time you want to put them back. But to be able to process your image independently, the star layer and the nebula layer is oh so powerful when it comes to processing a deep sky image. So LRGB imaging, if you're not familiar with that term, you're shooting with a monochrome camera, black and white, through LRGB filters. So red, green, blue, and luminance, which is basically just the white light. So what I was surprised to find that from the city is that this approach, LRGB imaging from a light polluted sky, actually works really, really well. And it's because when you look at the spectral graph of those RGB filters, these happen to be the astronomic type, it really does isolate those areas of the spectrum where you're going to find those colors and cancels out a lot of the others that you don't. As opposed to if you shot unfiltered, of course, that wavelength is just capturing everything. So that isolation per color channel is enough to overcome light pollution in my case. And I highly recommend giving it a try. A lot of people think that you would have to shoot stacking a light pollution filter on top in front of these RGB filters, but it's not the case. So that image of the Whirlpool galaxy taken from my Boreal 7 backyard is a proof of that concept. So some tips for shooting in broadband RGB true color images. If you can, like I just said, shoot with a monochrome camera. You're going to get a stronger signal than you will with one-shot color that's dividing that signal into those color buckets of an RGB filter. One-shot color unfiltered is possible, but you're really going to have to work added in the processing. So, you know, if your image processing skills aren't strong, I wouldn't recommend trying to dig out an image from an unfiltered shot from the city. You know, historically, I've always used these light pollution filters and swore by them, imaging from the backyard, to just help separate the object from the sky. If you're looking for a mild broadband filter, like the Optilong L Pro is the one I continuously recommend and still use today after 3 years. It just does a great job. So as I mentioned, the challenges are those gradients and the color balancing. It's not uncommon to see, you know, an orange wash over the entire image from the long exposure images of the night sky, of a light polluted sky. Often you'll see the image look very green, as you did a couple slides ago, just due to the sensor of that color camera. It's recording RGGB, so twice as much green. So you really have to adjust those colors and as I said, dig the image out sometimes. So there's a before and after of IC2118, I believe. It does have a name. I can't remember what it is right now, but that's, as you can see in the top image, it just wasn't even, I had to, you know, just have blind faith that it was actually in there before I processed it, and know that my Mount star alignment was correct. But sure enough, it was there, and it took a long time to process out. So specific tools for removing those gradients. There's Gradient Exterminator, a great third-party tool for Photoshop. It does a great job. And then there's the even better Automatic Background Extractor, which is one of the tools, processes in PixInsight. It does it better than anything else I've ever used. So PixInsight is something that takes a long time to learn. I'm still getting up to speed myself, but that was a real game changer, that Automatic Background Extractor tool. And then using masks is something you're going to have to get used to if you want to start controlling the areas of the image you wish to manipulate and stretch, and the ones that you want to leave alone. An example would be, you know, you want to sharpen an area of dust or clouds in your nebula. You certainly wouldn't want to sharpen black areas of space that may already be noisy. So just as an example. So narrowband imaging is really you know, advantageous from the city, because you are blocking out so much of that unwanted light. In the example spectral graph there, that's the hydrogen alpha bandpass of 656 nanometers. And as you can see, you are really isolating that specific light. So in the case of Melat 15 here, you can see in that grayscale small image, that's just the hydrogen alpha there. And then to create that full color image, I shot it in O3 and S2 as well. So there's all these different color palettes that you can you know, display your images in to represent different gases. The SHO color palette, or the Hubble palette with those blues and golds is a fan favorite. I certainly love it. Lots of options for mixing the colors when you do isolate the gases and map them to specific colors like that. So H alpha, the great thing about when you are isolating a very narrow band passive light, the way I have with the H alpha there, you can do that on a moonlit night very successfully. You will need to shoot longer exposures though with these narrow band passes, because as you can imagine, you know, you're really isolating the light you're collecting, so you need to expose longer on these often dim areas. So processing tips for narrowband, monochrome camera is almost a must, but it can be challenging in those narrow band passes to actually see your object in a single exposure because it is so faint. So I suggest shooting through that hydrogen alpha filter specifically. Usually that has the strongest signal, and then you can just switch filters and do your O3 and S2 in that same area once you've confirmed and framed things up using that H alpha filter. So just a little tip there. But it takes a lot of time. You need to build a full color image. You don't have that instant gratification that you do with a one-shot color camera that produces a full color image in one shot. But it's well worth the time and effort because you can create even more dynamic images. Balancing those channels of specific band passes of light carefully takes time too, because you'll find that some of the some of the data is much stronger in certain signals than others. So you'll often have to pull that oxygen up, bring the hydrogen alpha down, stuff like that, to create a balanced image that showcases the object in the way that you want to, as is the case here with the Seagull Nebula. Some specific tools that are handy at this stage are the Correct Magenta Stars tool, script in PixInsight, and then the SCNR green removal tool in PixInsight is another really powerful one. Just in case anyone's at that level and they're looking for some tips there, those specific tools are very handy. Here are my ninja processing tips. What I found is that if you blend your multi-band pass color data, so one-shot color camera and those multi-band pass filters, with your narrowband data, you can create these really fascinating images with a lot of depth, like the image you see there of the Eagle Nebula with the pillars of creation highlighted. The more signal you collect and the more you can create separation between the light that's emitted in these objects, the more depth you're going to get, and the more you'll be able to control the variations of color and the gases in these nebula. So you create these one-of-a-kind images. There's a tool called deconvolution in PixInsight, which I avoided for so long, just the name scared me, to sharpen important structures of a nebula or galaxy. So it's essentially a sharpening tool, but to really maximize its effectiveness, you'll want to use layer masks in Photoshop. And all those are basically selecting the areas of the image you wish to adjust from the ones that you don't. So as I mentioned, where certain areas, in this case the pillars of creation, I sharpen them up much further than I would say the layer of just the stars themselves. I want the stars to remain soft. I want the pillars of creation to be sharp. So that's where the masks come in. And that black and white image you see there on the bottom is an example of what the masks look like. And you can tell it's masked the brightest areas of the image. The white area is where we're going to select, and the black is where we're going to leave alone. So in this case, we'd be leaving that black area alone, perhaps performing some noise reduction to that area, and then sharpening the brighter areas. But you can really fine tune those masks. StarNet++, I briefly mentioned before, is extremely powerful here because it, of course, separates the stars from your image. So you can process them independently from one another, because usually you want to adjust those stars in a different way than you would want to adjust the structure of your nebula. Final slide here. I hope I haven't went too long and there's time for questions. This is something that's very exciting to me and how I've kind of committed to my astrophotography in the backyard. That is an observatory I recently put up. It was a long time coming. It is called the Black Dog Observatory, named after my faithful companion, Rudy, who is very proud to have that name. And yeah, so that's the latest from the Astro Backyard. And if you want to follow everything that I do, I share absolutely everything. You can follow along on the Astro Backyard YouTube channel and astrobackyard.com blog. So that's all I have, and hopefully there's some questions.
Thank you very much, Trevor. Fabulous presentation, great images, and it's really amazing the before and after images, the kind of detail that you can pull through processing. Really well done. Let's go to Emma for questions.
We've got a few questions for you. First question is from Super Creative. Is doing RGB stars worth it for an HOO or SHO image? And do you do it?
It is. Okay, I love that question because I know we have a more advanced crowd. Yes, it is always worth it to shoot RGB stars. I think so anyway. So the reason that question is so smart is because something I didn't mention, when you shoot using those narrow bandpass filters, you're essentially going to create an image with white stars. But if you shoot in broadband, that's where you'll collect the natural star colors. So what a lot of astrophotographers will do is shoot exposures in broadband RGB, often shorter exposures, just to get that layer of colored stars. And I think it's always worth it. Due to time constraints and cloudy skies, I would say I rarely get to it, but it's always worth it if you have the chance to capture the beautiful real star colors in your deep sky object.
Thank you. Lewis wants to know, do you do any post-production, so to speak, where the filter that you used did not give the shot you expected? And do you use any software other than Photoshop?
So yeah, in terms of post-production on the images, shooting with those multi-band pass or the narrowband filters, a lot of times, yeah, you will see an image that's almost close to what the final image will look like in a single exposure. But 80% of the time, it's just, it's absolutely buried in there. So there is some serious stretching going on. And when I say stretching, I mean that, areas of the midtones and the highlights come way up, the highlights not too much, and keeping those dark areas down. So if you think about the histogram and your data, you know that it's in there, but I'm doing some very strong S curves, if for those familiar with that, to actually bring that data way up. So all of my images are quite heavily processed for sure.
This question also comes in from Lewis. How often do you do unplanned photography?
Ooh, unplanned. Well, I guess if it's a surprise clear night, yeah. Oh, you know what? In the case of last year when we had Comet Neowise, it to me it felt like it came up overnight in terms of its availability to photograph, and that's something I certainly didn't plan months in ahead to photograph. And it was so exciting and so memorable to shoot something new like a comet. And yeah, so that was very unplanned. And stuff most recently like the partial solar eclipse. Again, that was all these astronomical events are very reactionary because sometimes it's a very limited window of opportunity and you don't know if it's going to be cloudy or not. So most of my unplanned shots are astronomical events like that.
Thank you. Ward wants to know, if you don't have access to a mono camera, would putting a color DSL into mono mode to do filtered imaging work as well?
It wouldn't work as well, but I've heard a lot of people say, it's a waste of time to shoot narrowband with a color camera in general. I found that not to be the case, specifically with the hydrogen alpha. I think you can use a color camera to collect really impactful, dramatic hydrogen alpha details on a moonlit night with your DSLR camera or a color camera and add those to an existing color project. As for converting a color camera to monochrome, I'm not sure of the entire process there, but I would think that you don't actually get that 4 times as strong signal as you would with a dedicated monochrome sensor.
Andy wants to know if you use Mac, PC, or Linux.
I use PC, and unfortunately for some, I find that the astrophotography world, at least in terms of software, is more PC friendly. So I know a lot of creative professionals use Mac computers. So it's unfortunate, and it is getting better. But for some of the tools, you have to come up with a workaround to use your Mac. But luckily for me, I've been a PC user from day one, and I'm too old to switch now.
This next question comes in from Alan. If there's one filter for astrophotography under the urban skies you would recommend, what would it be?
The two that come to mind, in this hobby, there's no one answer for anything, but the two that come to mind are the Optolong L Extreme and the Radian Triad Ultra. The L Extreme is much more affordable. For if you like shooting emission nebulae and you have a color camera and you're under light polluted skies, you can confidently get that L Extreme filter and thank me later.
Lewis wants to know, do you license your photos to the Photoshop or PixInsight databases or others like National Geographic?
No, I don't. It's something I've thought about and maybe will pursue in the future. But my images, other than being shared as a reveal at the end of one of my YouTube videos, don't really go many places. I don't, I've submitted a few NASA APOD images and got the one, but I really don't do a whole lot with my images and don't license them. But it's worth looking into. I guess the real reason I don't is because I'm never truly satisfied with my final image, and it's not done yet, and I'm not ready to, it has to be perfect before I go that far with an image. And I maybe only 2 or 3 of my images have ever got to that stage.
You taught the Canadian Astrophotography School's program in 2019. Do you plan to teach this program again?
I don't plan to. I suppose if they asked again, I would consider it. It is a lot of fun to do a hands-on face-to-face workshop. It was, unlike anything else, it was nice to be able to teach a class in person, but then be able to, come up to individuals and help them through the issues they're having. Because, when I'm doing these YouTube tutorials and explaining things, there's no feedback. So if I'm going too fast or you're not explaining something properly, I don't know until after it's over. So the live classes are really nice. So yeah, I would do it again.
Thank you. This is the last question coming in from Robert. How many subscribers do you have on your YouTube channel now?
Last I checked, it was 271,000.
Wow.
Yeah, the YouTube is such an interesting thing, and really what it comes down to is being consistent and being dedicated to it. I've been making videos for 5 years, and early on, very few people were watching, but I was just as excited to make them back then as I am now. So, so much fun. I can't believe how far it's come.
That's great. That's all of our questions. So back to you, Paul.
Trevor, before we let you go, I actually have a question of my own. When you're shooting a monochrome LRGB, what is your typical single exposure length?
Typical exposure length for my skies is about 180 seconds. I'll do 3 minutes in each color filter. Mm-hmm. And then the luminance will either be about the same or maybe even a little longer. But I kind of play it by ear. Depends on where the object is too. So because I have that great view to the north, for example, that the Whirlpool galaxy kind of hanging around Ursa Major and the Big Dipper, I could shoot those 3 minutes successfully because it was out of the light dome and kind of in a darker spot, but usually around 3 minutes.
Okay, good to know. Thank you very much. Great. Thanks again for a great presentation. And that concludes the speakers lineup for this evening. Thank you again to our 3 speakers. And let's go to Tom Luton, our president, with the announcements.
Thank you very much, Paul. Good evening, everyone. Hope you're all doing well this summer. And don't have my screen. Okay, right, trying this again. Okay, so evening, everyone. Hope you're doing well. And let's get right into the announcements. So this is one of 2 types of meetings that we have here online. During the summer months only, we have, or during year-round, we have our recreational astronomy nights. And from September to June, we have our speakers nights. Now, so our next speakers night won't be until September. If you're here for the first time, please say hi in the YouTube chat, enter some questions for our presenters. If you're a new member, introduce yourself. And if you're from far, far away, let us know where you are from. For example, I am right now speaking to you from Cobourg, which is about an hour's drive east of Toronto. So our next recreational astronomy night is on the 4th of August. Andy Beaton will be discussing the sky this month. Ron McNaughton, weighing the Earth 2.5 centuries ago. And we have space for one more presenter. If you'd like to present, please contact Paul Markov. Arnold spoke a little bit about observing certificates earlier on. Here they are again, the full list. Explore the universe, explore the moon with binocular or telescope, the Messier catalog, our finest NGC, double stars, the Isabel Williamson Lunar Certificate, Deep Sky Gems, Deep Sky Challenge. If you'd like more information, www.rasc.ca/certificate-programs. Our education and public outreach activities are moved completely online, but we have been planning and have had virtual star parties and EPO talks with Ontario Science Centre, Millennium Square, the David Dunlap Observatory, St. Clair O'Connor Community, the Dunlap Institute, with Brownies, Cubs, Scouts, and school groups, and as part of our new Observers to Visual Astronomy course. More details available at publiceducation@rascto.ca. Because of the pandemic, our observing sessions at Baby Village Park, at Long Sault Conservation Area, and Ontario Science Centre are suspended until further notice. But I do have some good news. Starting July 3rd, we are accepting online reservations from campers, day users, and modal and locker leaseholders for the Carr Astronomical Observatory near Collingwood. At this time, we are not accepting reservations to stay in the house. We've got some COVID-related safety renovations to complete before we can do that. The Sue Laura Observatory is open. The Jeff Brown Observatory is still closed. Full details for booking are on the website, and please read those details before you make your booking. We've got some volunteer jobs open that we're trying to fill right now. Our observing committee chair and some committee members, our light pollution committee chair, our national council representative. We're looking for marketing committee chairs and committee members. Our AV committee, who worked so hard to produce this wonderful show, needs some additional help. We need more folks to help out with education and public outreach, and also some telescope camera operators for our virtual star parties. If you can help, please drop a note to volunteer@rascto.ca. Our Stellarium courses are popular. The Level 1 course that is being taught by Al for July 12th is full. The Level 1 course hosted by Kirsty for July 13th is full. Level 2 course hosted by Blake for the 19th is also full. We've got a Level 3 course coming soon and a Mobile Plus course coming soon, and we can add you to our waiting list. More details, rascto.ca/content/Stellarium training series. This is the part where I get to plug RASC membership. So please sign up or renew online at secure.rasc.ca. If the COVID pandemic has thrown you for a loop, we can help out. The RASC does have an emergency fund. It's completely confidential. If you'd like to talk about that or to talk about giving a gift membership, you speak to Adela in the national office at mempub@rasc.ca. And that brings us to the end of the night. I'd like to thank you very much for joining us. Please visit our website, rascto.ca. Please follow us on all forms of social media. If you liked the video, please like and subscribe and hit the notification bell. Be safe, keep looking up, and have a good night.